Hello, I'm Professor Paul Bingham, and this is Biochemistry 1. Our purpose in this segment is to take the first important steps toward your mastery of an understanding of two crucial proteins, hemoglobin and myoglobin. They're important not just physiologically, as you'll see, they're crucial to the fact that you and I are alive and breathing, but they're also extraordinarily important to the development of biochemistry historically. The proteins are abundant for reasons that will become apparent momentarily, and easy to get hold of in large amounts, and so they were among the first proteins that we ever really understood well. And we're going to argue over this segment and the following connected segment that the lessons we learned from these well-studied, originally studied proteins ramify throughout all of biochemistry and teach us more general lessons. So remember, our overall goal in this segment of our journey is to understand how the molecular machines encoded by genes, the proteins, the evolved molecular machines, the fine-tuned by natural selection molecular machines, how they work. And today, and in the following segment, we're going to dig a little more deeply, not just into the function of individual monomeric proteins, as we have in several segments before this, but we're also going to begin to look at how multiple different monomeric proteins get together to form functional multimeric proteins that have some additional attributes that most monomeric proteins don't have. So what we're going to do is start with a monomeric protein, myoglobin, and then go to a closely related multimeric protein, which has multiple myoglobin-like subunits, and understand what myoglobin can do and what this multimeric hemoglobin molecule can do differently that myoglobin cannot. So this is a slightly busy slide to remind you of things that you've known since you were a child about how the circulation works. So the heart takes blood returning from the tissues depleted of oxygen and pumps it out through the pulmonary artery to the lungs, where you're breathing, and the lungs are rich in oxygen. The blood picks up lots of oxygen, turning coded red here, partly because the proteins that carry oxygen turn redder when they bind oxygen. That blood comes back from the lungs to the heart and then is pumped out to the tissues, as you can see at the bottom. And then at the right-hand segment of this image is a blow-up of the tissues themselves when the blood gets delivered there. So the arterial blood, coded red here, comes in and it pumps oxygen-rich blood into the capillary network symbolized in the center of this right-hand image. The tissues then extract oxygen from that blood, turning it blue, so to speak, that is, making it more oxygen poor, returning it now to the venous side on the blue vessel here to return to the heart and complete the cycle. Let me call your attention to where the two proteins that we're going to focus attention on today reside. So myoglobin, as you might imagine from the spelling, muscle, myoglobin is in fact a muscle protein. It retrieves oxygen from the blood, holds it, helps it diffuse and disperse through the muscles to drive metabolism. As we're going to talk about later in the course, a lot of our metabolism, a lot of the energy that we use to think and to move and to perceive is derived from oxygen-dependent metabolism, chemically analogous to burning a newspaper, for example, in the presence of molecular oxygen in the air, as we'll see later. Today, all you need to be aware of is that the continued supply of sufficient amounts of oxygen is absolutely crucial to the function of all the organs in your body, including obviously your mind. We're going to be focusing today, though, on the muscles, because the muscles are so occasionally burn so much oxygen that they have the specialized carrier protein myoglobin to capture blood from the circulatory system and help disperse it efficiently through muscles that have, again, extraordinarily demand for oxygen to keep going. On the other hand, hemoglobin is in red blood cells, symbolized here by the red ellipsoids. Red blood cells, it captures oxygen in the lungs and then gives it up in the tissue. As you might imagine, that's a slightly more complicated trick than just grabbing it the way myoglobin does. And as we'll see, hemoglobin has evolved by natural selection to have some really remarkable capabilities that make it good at this trick. But it turns out to be much easier to understand hemoglobin, the multimeric protein, if we start with myoglobin, the monomeric protein. Again, remember that they're evolutionarily related, so that when we go through the structures of myoglobin and its functional organization, all those lessons can be transferred wholesale to hemoglobin. So we're really talking about both hemoglobin and myoglobin in the next couple of minutes when we talk about structure and function of myoglobin. So let's look first at its elementary structure. So this is just a conventional ribbon diagram of myoglobin. And let me walk you through several several of its essential features. So this is the N-terminus of the myoglobin molecule, and beginning at the N-terminus, it's conventional to label these alpha helices, both in myoglobin and also in hemoglobin, in a standard way and refer to them in that way. So this is alpha helix A, B, C, D, E, F, and G. And as you'll see, a couple of these helices are going to play a direct role in the functioning of this molecule in ways that will emerge over the next couple of minutes. And I'm sorry, I forgot to add the H helix here. So the E and F helix are going to play a particular role in organizing the functional component of this molecule, the heme prosthetic group, as it's called. It's from the same root as a prosthesis, right? A replacement limb. The notion of this is that the protein itself is not capable of doing the sophisticated interactions with oxygen that are needed here, and so natural selection has recruited a non-protein group, a prosthetic group, to be the business end of this binding protein. We've seen similar things earlier in the context of coenzymes, for example, with catalytic molecules. This oxygen binding molecule is going to do something similar, and we're going to look in the next couple of minutes at the structure of that prosthetic group, that heme prosthetic group. So let's blow this bit up. And right in the middle, drawn now as a stick diagram, ball and stick diagram, rather than as a ribbon diagram, as the helices are, you'll see I'll walk you through both the heme prosthetic group and a couple of the amino acid side chains that are involved in interacting with, immobilizing, and allowing to function in some surprisingly sophisticated ways this heme group. So let's look at that heme prosthetic group close up. So there is the prosthetic group itself. It's a little complicated in this diagram to understand. I'm going to pull it out and we're going to look at it in isolation in just a moment. Here is that heme prosthetic group. This prosthetic group looks a little complicated at first glance. It's a little more complicated, for example, than an amino acid, as we've looked at before. But stop and look for a minute. It's not hugely more complicated. It's made up of 4 copies of what are called parole rings, and so its synthesis, as you might imagine, is comparatively simple. Each of these parole rings is linked by what organic chemists sometimes call a methane bridge. And then let me call your attention to the fact that each of the parole rings has a nitrogen on it. And those parole nitrogens are engaged in coordination complexes with the central iron ion, the oxidation state +2 iron ion. And that iron atom will be absolutely central to the binding of oxygen, the reversible binding of oxygen, as you will see. Let me show you a slightly different view of this molecule. Before I leave this, notice at the left the word porphyrin. Porphyrin is a generic term for this kind of structure. Hemes, and there are several other porphyrins that will show up later in our journey that have the same fundamental structure, but some of the peripheral substituents, which we haven't talked about here, are different in heme and some of the other porphyrins, and allowing them to interact very specifically with the particular proteins that they need to interact with as functional prosthetic groups. So let's look at a slightly different view of this heme prosthetic group and introduce a couple of other players. Okay, so there is the central iron atom. Keep your eye on that. That's the real business end here. So here is now a different view of a heme group. It's just kind of laid out in slightly in perspective. And what I want to call your attention to is the oxygen bound at the top, the diatomic molecular oxygen, is forming a sophisticated coordination bond with iron. This is actually very advanced inorganic chemistry. We won't talk too much about the details here, but I'll call back later the fact that when iron binds, there's some exotic electron sharing that changes slightly the size of the iron ion. So the oxygen becomes superoxide-like, having an extra electron, and iron becomes iron 3+, like giving up an electron partially to the oxygen. Again, a rather exotic bond. The details of that in organic chemistry aren't of terrible concern, except for 2 things. That bond is reversible. The oxygen can give back its electron and move on. And in addition, the size of the iron ion is going to change. And as we'll see later, that turns out to be quite profoundly important. All right. Notice also this histidine. I'm going to show you where that histidine comes from in a moment, but obviously it comes from the myoglobin protein. It's a side chain sticking out from one of the particular alpha helices, again, as you'll see in a moment. So this is now a different view with slightly more detail of